Hello everyone, I'm Jaehoon Kim from Hanyang University. Today, I'll be presenting RAPS, automating hypothesis-driven statistical analysis of public survey using large language models. This work was conducted in collaboration with Dayoung Jeong, Beejin Son, Professor Hansung Kim, Professor Bogoan Kim, and Professor Kyungsik Han. I'd like to begin by providing some background. Public survey data is crucial for understanding social dynamics in health, education, and beyond. As data accessibility grows, social scientists increasingly rely on these datasets to drive public policy and academic research. So, how do social scientists actually analyze this data? It's usually a three-step process. First, formulating a theory-based hypothesis. Second, operationalizing abstract concepts into measurable variables. And finally, applying statistical models to test them. While this process may appear straightforward, applying it to massive public datasets introduces significant challenges. Through iterative discussions with domain experts, we identified three key challenges and corresponding needs. First, we observed cognitive overload from hundreds of inconsistently structured variables. Second, we found a lack of structured tools, making reproducible planning very difficult. And third, general purpose LLMs are often too unpredictable. Researchers need bounded evidence based tools, not just open ended text generators. These needs lead us to formulate three design goals. Goal 1: create a conceptual search space where an LLM suggests variables with reasoning, allowing researchers to refine their operationalization. Goal 2: provide an analytical decision space to structure methodology for transparent review. And goal 3: constrain the AI's functionality to a strictly domain-bounded workflow to ensure trustworthy results. Based on these design goals, we structured system functionality into 4 steps aligned with the hypothesis testing procedure. RAPS consists of a total of 9 LLM agents. In step 1, operationalization, 4 agents work together to map abstract hypotheses to concrete survey variables, realizing design goal 1. Step 2, planning, uses the data descriptor and analysis planner to structure the statistical methodology, realizing design goal 2. Step 3, execution, employs the code generator and debugger to produce and validate analysis code. And step 4, reporting, generates comprehensive reports through the report composer. The entire workflow is constrained within a domain-bounded pipeline, realizing design goal 3. Let me briefly demonstrate how the system operates. In step 1, RAPS automatically identifies suitable variables. Crucially, the user maintains full control through the conceptual search space. User can review, add or drop variables, like in this demo, where the user requested to remove the age variable. In step 2, RAPS provides the data and suggests a structured statistical plan. User can review and update the plan through the analytical decision space. As you can see here, the user successfully updated the plan to use a logistic regression instead. Steps 3 and 4 handle execution and reporting. RAPS generates analysis code automatically debugging any errors. Once successful, it creates a report complete with p-value, effect size, and interpretation. Finally, the system log records every operation for transparency and reproducibility. To validate RAP's technical soundness, we tested it against 5 textbook exercises for complex survey data. RAPS produced identical results across all 5 exercises. Here is the overall flow of our study. We employed a within subjects design where everyone experienced all 3 environments, the baseline, the general LLM, and RAPS. We fully counterbalanced the order to prevent running effects. We measured usability with SUS, cognitive workload with NASA TLX, and trust in AI with TXAI. Finally, we concluded the study with a semi-structured interview to dive deeper into their experiences. We conducted this 2-hour study with 12 social science researchers. Our results show that RAPS achieved significantly higher usability. Participants highlighted two key themes. RAPS serves as a collaborative tool that preserves the researcher's control. As P3 noted, I could revise and adjust variable selection and the analysis plan, and it always felt like the true RAP made decision to me. RAPS raises the baseline of analysis quality. P7 remarked that a tool like RAPS would let students or researchers try more kinds of studies and make research more accessible. For cognitive workload, RAPS showed substantial reductions compared to both environments. Again, two key themes emerged. RAPS reduces the cost of explanatory analysis by making early analytical conditions visible. P11 described RAPS helps reduce the cost of testing analytic idea quickly, allowing me to check whether an analysis is feasible with the dataset before committing to a new method. RAPS enables researchers to focus on conceptual decision rather than tool management. P5 noted, RAPS automatically organizes everything I used to stitch together on my own. It freed up mental bandwidth because I didn't have to manage the process myself. Regarding trust measured by TXAI, RAPS scored significantly higher than the general purpose LM environment. The key theme here is that RAPS builds confidence through transparent domain-bounded reasoning rather than black box recommendations. P2 explained, with general LMs, I often felt anxious about hallucinated variables or arbitrary statistical choices. RAPS, however, clearly grounds its recommendations in the actual survey metadata, which made me trust its output. P10 mentioned because the system explicitly explains why it chose specific variables and statistical methods, I didn't feel like I was blindly accepting the AI's answer. It felt like a transparent collaboration. This leads us to three design implications. First, RAPS mitigates analysis quality variation, but novices may still overlook essential data verification steps. We propose reconceptualizing data cleaning as visible, traceable decisions and providing reflective cues to maintain data literacy. By explicitly exposing these analytical choices, we can prevent the descaling of novice researchers and foster a more critical engagement with the data. Second, while RAPS sustains a coherent workflow, researchers occasionally need an external theoretical context. We suggest integrating on-demand show evidence features to link analytical choices with literature. This integration would transform the AI from a statistical tool into an integrated tool that bridges the gap between data and the domain. Third, since meaningful interpretations inherently vary across disciplinary traditions, we suggest a cross-domain simulation agent that presents diverse perspectives while preserving researcher agency. Such an approach will support the multidisciplinary interpretations essential for robust social science research. We also discussed two considerations. First, strict AI safety filters sometimes block legitimate analysis of sensitive survey topics like mental health. For example, the Youth Risk Behavior Survey containing items related to suicide tended to fail analysis at times, depending on the type of LM model. We need to better balance safety policies with research robustness. Second, procedural transparency still relies on human ethics. We propose automating audit trails and workflow logs to facilitate transparent, evidence-based reporting, supporting accountability without replacing it. Such features can contribute to the promotion of transparent research. For more details, please refer to our paper. Thank you for listening.